apologize that we're having to do it remotely this morning, but still having some breathing issues. And so COVID test came back negative, but just so I wouldn't scare anybody with my coughing. So the test, we'll get started there. The test should be graded. Your grades are up online. Did pretty well. There were 3 questions that I was surprised by the results. So they weren't so bad that I threw them out. They were bad enough for me to give credit for them. So if you got those right, you could think about it kind of as a bonus. If you didn't get those right, then you're held not accountable for those. So everybody got a 10.5 adjustment. I also did, I threw out the second question, identical question. That was my copy and paste error on there. I just went ahead and made it by 29. So it's a little different. It turns out that 29 questions is 33.44 a question. So instead of being that accurate, I just added, so 3.55. So on this exam, you got a little bit of a round up error, a round up bonus, and then everybody got a 10.5 because there were 3 questions that were a little tougher. So that's exam 2. I'm gonna try and scan those and get those back to you today, either today or tomorrow, but I'll do my best to try and get it back today. Okay, so where we ended off, so let's go ahead and move forward. So where we ended off was in elimination. So all we did was cover the basic mechanisms of E1 and E2. So we want to talk about a couple of things today and then move on into alkynes. So one of the things we need to look at when we're looking at reaction, predicting the products of a reaction, is to look at the stability of an alkene. So if we think about just a simple E2 process, and we have potassium T-butoxide, and some type of solvent, we actually have 2 possible products. If we think about an SN2 type product, an E1, so here we have E2. If we look at H2SO4 and we have an E, and we have an E1 process, again, we have multiple possible products, right? We could get this one, or we could get this one, okay? So we need to think about the stability of the alkynes to help us predict the product. So if we look at the first one, we have a difference between a trans alkene and a cis alkene. In the second one, we look about it, we have a mono-substituted, right, versus a tri-substituted. So this is the stabilities of these will determine the product. So in the first one, we notice the E2, we have both the hydrogen coming forward, hydrogen going back. We haven't designated the bromide, so the selectivity of the antiparaplanar is not going to give us the products. So we have to look at the stability. So in general, the stability of alkynes is going to be mono-substituted is less stable than di-substituted, which is going to be less stable than tertiary substituted, which is going to be less stable than quaternary substituted. So here we have the most stable, right, and least stable. This has to do with a experiment. If you take these and you put them in hydrogen and palladium, which is a reaction that we're going to look at very soon, that's going to be in alkenes. what is the energy required to do this, or what is the energy that comes out of it? And so when they did that experiment, what they found is that the one that takes the most energy is the most stable. So that's the tetra substituted. So if we look at primary substituted, secondary, tertiary, and quaternary, and what we're looking at here is the idea of looking at what is attached. Right, so if you circle your double bond, it's simply just how many different things are attached. So we have two things attached, right? So that's going to be a disubstituted or a secondary substitution. The other aspect of alkene stability has to do with spatial arrangements. And in that case, we have the trans and we have the cis. Right, so if we think about the trans, you've got your methyl groups on opposite sides. And then cis, you've got them on the same side. Because of this interaction here, right, that's going to make the trans more stable. Okay. Questions about those? So when we're looking at a reaction, okay, we're going to end up with several products. And the way to think about it is, since there's free rotation around this acyclic, so around here, right, I can rotate around that bond, I can rotate around this bond. That means I can always get antiparaplanar. I've got an E2 type mechanism. So what we're going to end up with is several products. Okay. So we get 1, 2, 3 different products. Right, so we have the mono substituted here, or the primary. We have the disubstituted and the disubstituted here. Between these two, we have a trans and a cis. Right, so this one's trans substituted. This one is cis substituted. So if we looked at ranking these, this would be most stable, secondary, and third, and that would be the order of our products. So our product order, this one would be the major product because it's the most stable of the possibilities. So that's one of the things you're going to look at as we continue to look at elimination, is looking at what's the most likely product or what's the majority product from eliminations. And you'll look at two things to do that. To figure out what's the most likely products in an E2, you're going to look at one, the stereochemistry, right? So if it's an E2, that stereochemistry has to be very specific. And then two, you're going to look at the stability of the product, which of course in eliminations means the alkene. With E1, stereochemistry doesn't matter, but you should always start there. So either whether it's E1 or E2 mechanism, you start with, is there any stereo specific that control that's going to limit the number of beta hydrogens that'll be abstracted. And then from there, you look at stability of the products, the alkene. when we looked at SN1 and SN2, there was a pretty straightforward comparison about which way to go on most of these. So if we look at E1, right, the first step of the mechanism is forming the carbocation. And then once we form the carbocation, right, the base comes in and forms the alkene. For E2, right, the base comes in and we do that all in one step. So this comes in and pulls a proton. So the base comes in, pulls a proton, electrons go down, we end up with a double bond. Okay, on this one, you know, we have the hydrogen here. Base comes in, pulls the hydrogen. So what favors E1 is going to be something that can form the substrate needs to be able to form a stable carbocation. In general, we don't need a great base, just need a base. And then just like before, polar solvents, and high temperatures, right? So we got to form that carbocation. If you notice, this looks a lot like the SN1, and we'll get to that in a second. If we look at E2, the only real thing that we need to watch for E2 substrate is that we can form an anti-paraplanar beta hydrogen arrangement. If we can do that, then most anything else works. Okay. We do need a good base. So, you know, we can't deprotonated. The reaction starts by the base. The bases need to pull that proton. The base instability. So we need a good strong base. Here, solvents really don't matter. It has little impact on it. We can say polar aprotic, but again, that's more because that slows down in E1. And then here, you know, moderate temperatures. So sometimes it's going to be pretty straightforward what the reaction is, but often the problem with these reactions is, let's say that I just put in a decent base here, or let's put in a good base. You know, this one most likely is going to go through E2. I've got a strong base. And so the easiest way to think about these is the ones that you know are going to be E1 or E2, and not worry about the ones that you're not sure about. So if we look here, that's going to be a strong base. We've got a secondary carbocation that's not stabilized, so not E1 style, right? So no carbocation stability there. And so this one is going to go through an E2 type process. I've shown the product here, and from this substrate, they're both the same. Now, if I change that to something like this, right now, I'm going to be focusing more on E2. I've got a tertiary group, right, which means possible carbocation. I don't really have a good base. I have an acid. Right, and I'm showing heat. What's going to happen is that this one is going to form the same product, but this one is doing it through an E1. If you're this type of reaction where we're getting dehydration, okay, this specific reaction, kind of like we did the solvolysis with the SN1, SN1, solvolysis is almost always S1. So solvolysis by definition is an S1. Here, this dehydration with an acid, either sulfuric acid or phosphoric acid, is going to give us E1. Okay. We can also determine E1 and E2 from the products. Right, and we looked at this one. Get rid of this trademark. Okay. So in this case, right, we all know we only get one product, so this must have been E2. We also have the consideration that we might have something like this. You know, we can make a very stable product. Here, if I used, again, kind of a decent base, with some heat and got that product, here, because this is a secondary stabilized, that means E1 is possible. But if we look at the reaction distance, I have a strong base. That suggests E2. For creation of this product, E2 and E1 are both potentially possible. Right? So here's a situation where from my reaction mixture, I'm going to get a mixture of both of those. Now, that's usually not a problem when we're doing synthesis, because in this case, both E1 and E2 are going to give us exactly the same product. So with SN1 and SN2, we had a little bit more distinction about which mechanism is going to occur. Other than a few examples of like the dehydration of acids or specific tertiary groups, or cases where my product shows me which way is going, E1 and E2 are, let's put it this way, it's hard to get an E2 not to occur and only get E1. The best example is the dehydration of an acid. So we often get these occurring together. And that's only a problem when the E1 product is going to be different than the E2 product. Okay. So there are some differences between the two, right? What we need. And there's some examples where it's going to be obvious that it's either going to be an E2 mechanism or E1 mechanism. But when we, and the products can specifically tell us whether it's E1 or E2 because of the stereo control. But in most cases, whether a reaction actually occurs E1 or E2 is not going to be essential to the synthetic process. So for making molecules, I'll set up the reaction to do an elimination, and it might occur versus an E2 or an E1. Here, I've got a strong base, so E2 is going to occur, but I can also form a carbocation. So if I added heat to this, I'm going to get some E1. So if I had to choose, I'd say E2, since it's the fastest, lower energy reaction, is going to be slightly favored. So whenever it looks like it's not clear cut with E1 and E2, it's probably not clear cut, if that helps. So in some cases, you're going to see very specific, right? Some cases you're going to not be able to form a carbocation. That's going to suggest an E2. Some cases you don't really have a base, that suggests an E1. And then always look at your products, because your products can help you determine E1 or E2. Okay? Now the reason that I left this afterwards is that we also have competition between substitution versus elimination. And in this one, let's start with an S&1 style reaction. So if we look at this reaction, right, the first step is loss of that carbocation, right? This is a tertiary group, right? So we can form a carbocation. And then we have a couple of things that could occur, right? And actually probably, so we don't get all confused on that, let's just move this down and look at those separately. So once we form that carbocation, my solvent, which is a nucleophile, right, but not a great nucleophile, can come in here and react with a carbocation to give me SN1. SN1 style product. Right? I could also have, though, the CH3OH could also potentially act as a base, not a great base, but a base. And with the carbocation, just like with the substitution, you know, that's and I can end up with the elimination. Because of the high energy carbocation, okay, it actually, both of these could occur. I could have substitution, and let's go ahead and finish this one out by having the methanol act as a base one more time. Again, it's a solvent, so there's plenty around. Okay. So we get this product, right? But since we're going through the carbocation, both of these are possible. Now, in this case, since I didn't add a really strong base, the substitution both substitution and elimination will occur because of the lack of a strong base, right? So if I had put methoxide in there, SN1 products will be favored over E1. And think favored, not eliminated. If I had changed the conditions to being, let's say, the methoxide in methanol, then the elimination product would be in higher concentration than the substitution. So the takeaway from here is, because of the carbocation, SN1 and E1 are almost always in competition. There's a few biological examples where the enzyme will only allow either SN1 or E1 occur. But in open solution, just open reaction, it's very difficult to only get an SN1 without some E1, and it's hard to get some E1, mostly E1 without some SN1. So when we're looking at this, because of this high energy carbocation, right, both of these become possible because this is the high energy species. So even if we have a weak base, right, it's going to potentially deprotonate. And even if we have a weak nucleophile, it could potentially attack the carbocation. We can change which one is favored by changing our reagent. So here we added a stronger base, and I favored E2. But if I think about it, even if this here can also be a nucleophile, so therefore I couldn't use this nucleophile, let's say, without that solvent, and force it to go only E1 in this process, right? So SN1 and SN2 are going to be in competition. That's not the same if we look at, let's say, a slightly different substrate here. Again, we have a secondary substrate, not likely to make a carbocation. In the first case here, I am going to get both products, the elimination and the substitution product, but the substitution is going to be favored. In the second case, and I should correct this. In the second case, I'm going to get elimination products, but very little substitution. Why is that in the second case? Well, here I've got a big, bulky base. Okay, so if I add a big, bulky base, I'm not going to get, excuse me. Excuse me. I'm not going to get the backside attack, right? Remember that our nucleophile needs to attack the backside of the anti-bonding orbital to give us the SN2 product. Here I've got this big bulky base, and it's not going to be attacking that side. We can also use non-nucleophilic type bases. Oh, and the example I wanted to use just escaped me. If this is incorrect, I'll send a correction. Sorry, I can't remember what I was. Okay. So here, if we look at this one, we can use a non-nucleophilic base and always end up with the elimination. There's not a long list of these standard ones, so I'll get those for you for Tuesday. I should have wrote those down before we started. So in SN2 versus E2, we have more control, which we should, right? It's going through a lower energy process. The way we control that is by controlling our substrate. If we have a small nucleophile, we're going to get mostly SN2 with very little E2. If we have a big bulky base, we're going to get mostly emanation with almost no, or just a trace amount, 1 or 2% of the substitution. We can also use specialty bases. They're non-nucleophilic bases that are going to pull the proton and give us the elimination. So in E2 and SN2, we can, by controlling our nucleophile slash base, determine what our yield is going to be. Okay, so if we have a substrate that forms a carbocation, right, we're always going to have competition between SN2 and E2, E1, SN1 and E1. So if you can form a carbocation, that's a high energy species, you always have competition between SN1 and E1. If you can't form a carbocation, right, and you use strong, good nucleophile slash bases, then you're going to get SN2. If you use a big bulky base, you're going to get E2, right? And if you use a non-nucleophilic base, you're going to get E2. Okay, so you have a little bit more control when you look at substitutions and eliminations. Okay. This one's a good one for lots of practice, so I'll try and put some practice up. This often causes a lot of anxiety. So think about the absolutes versus the nuances, right? There are some very good absolutes here, right? So if we think about E2 versus E1, right? If you have a strong base, E2 is going to be favored. E1 is still possible, but E2 is favored. If you have dehydration with an acid, that's going to be E1, right? You're not going to, you almost never see an E2 there, especially if you can form a stable carbocation. In substitution elimination, don't try and figure out whether SN1 or E1 is favored. They're almost always in competition with each other. So you could have slightly more SN1 than E1, but if the question was which of the mechanisms occurring, you're going to get both. And then for SN2 and E2, you can predict, and it has to do with the size of your nucleophile, right? So the size of your nucleophile, right? Big nucleophiles favor E2, small nucleophiles favor, nucleophile bases favor SN2, and then you do have a set, and there's only 2 or 3 of these, and I'll get these to you on non-nucleophilic bases. Okay, so let's change gears a little bit. We're going to look at alkene reactions. So if we think about an alkene, what we have here is a carbon with 2 p orbitals with overlap. Because those electron density is outside, this is available electron density. That available electron density means that this is going to act as a nucleophile. Now we had, one of the questions was that students seem to have trouble with was, does an alkene behave, is an alkene, it was a nucleophile base? Well, by definition, a nucleophile can be a base and a base can be a nucleophile. So we think of alkenes as being nucleophiles, but one of the first reactions we're going to look at is actually the reaction with alkyl halides. I'm not saying alkyl, we're forming alkyl halides. We're making the HBr. So here, if we have this reaction, what ends up happening is a bromine. Now we can think about this as nucleophile electrophile leaving group. We could also, because it's a proton, think about this as a base proton and leaving group. Again, if you have any questions, just post it. I know we're kind of going fast today. Okay. So what's happening here is that the nucleophile is attacking the electrophile, my hydrogen. So nucleophile attacks my electrophile, right? And my leaving group's going to leave. Now this forms a carbocation, right? So the electrons go to one side, to the hydrogen. And then the bromide comes back in and attacks that carbocation. And that leaves me with the HBr. Okay, so I've now made the alkyl halide. So there's a few things here to think about. First, we're forming a carbocation. That's going to be a high energy species, and the carbocation is going to need some regioselectivity. So if we look at this substrate, I could either form this carbocation by adding the hydrogen here, or I could have formed this carbocation, right, by adding the hydrogen there. Okay. So I have two sides where I could add the electrophile. So because of that, we're always going to have two sides where we can add the electrophile in alkene reactions. I need to consider the stability of my intermediate. Okay. In this case, this is a tertiary substrate, and this is a primary, sorry, carbocation. Right, which means this is going to be more stable. Right, the primary is going to be very unstable, so the tertiary is going to be my stable, which means it's actually this one that the bromine comes in and reacts with. Okay. Giving me this product. Okay. This is known as Markovnikov's rule. The way Markovnikov's rule is stated is that the group that's added is added to the most substituted side. That's because the carbocation is going to be formed at the most substituted side. So Markovnikov's rule is stated, if you read the book, is stated as the result of the product, but the result of the product is based on the stability of the carbocation. So when we're doing this, remember that you're adding the electrophile to one of two sides, right? In this case, the electrophile is the hydrogen. That then results in formation of the most stable carbocation. Okay? This is known as Markovnikov's rule, and will give us a substitution at the most stable side. We're also going to see something called non-Markovnikov products. The non-Markovnikov products is not going with the least stable. What we do is we have to trick the chemistry into adding the substituent to the opposite side. So we have regioselectivity here. That is based on the stability of the intermediate. So let's try that. I'll give a couple. You tell me which side is going to have the bromine. So let's take a second. Show me the products. Okay. Go ahead and show you this one. I always like to work these through with the mechanism. So nucleophile attacks electrophile, leaving group leaves. What this does is allow me to think about this and how it's happening versus memorizing, right? So I've got two places to add the hydrogen. I could add the hydrogen here, which would give me a secondary carbocation, or I could add the hydrogen here to give me a tertiary carbocation. Which one's more stable, secondary or tertiary? Well, tertiary. So therefore I want the carbocation here, which means I added the hydrogen there. Okay. Then the bromine, now that I've got that established, to get the product, then the bromine is just going to come back in, act as the nucleophile, attack the carbocation, which is our electrophile. And I know that I'm going to get my bromine here, right? And since it's a mechanism, I'm showing the hydrogen, but you don't have to. So if you showed the product with just the bromine, right, that would be the right answer. I've added the bromine to the more substituted side because the carbocation is more stable. So if you work through this systematically, you'll end up with that product. And the second one, I'm using aromatic here. And it's specific to know that aromatic is a different functional group than an alkene, right? So this is something that will come up several times. And remember that aromatic is not included in the alkene functionalities. So aromatic groups behave like that's because the aromatic, because of this ring, is much more stable. Okay. And what we're going to see when we get to aromatic reactions is that aromatic reactions tend to react with electrophiles, but they have to be much stronger electrophiles. So the electrophile here is not enough to react with that aromatic. So this is going to come out throughout this chapter and on, is that you're going to see aromatics that are just not reacting. It's not 3 double bonds in a ring, it's an aromatic. Okay. So that means that we do not have, this will not play a part in addition of the electrophile, but it does play a part in the stability of the carbocation. Okay. So again, I like to work through the mechanisms. So nucleophile attacks electrophile, leaving group leaves. Okay. That gives me 2 possible carbocations. I'm going to draw both of them this time. And drawing both of them, all it does is take a little space. Okay, both of these are secondary, but what's the difference? Okay, this is secondary here, this is secondary here, but this one is also stabilized, right? Because I can delocalize that into the aromatic ring. So that destabilization here means that my bromine is going to attack this electrophile, and that's going to be my product. Okay. So the residual selectivity of electrophilic additions to alkenes is going to be based on the carbocation stability. Of course, I've shown HBr here. HBr reacts like HCl, reacts like H iodide. Right. The only one that's a little different is HF. You don't see that one. Fluorine chemistry works a little bit differently. Okay, questions about electrophilic additions with HBr? Another reaction that we have is hydration. This is a symmetric alkene, so both sides will be the same. What's happening here is I'm adding H3O, I'm adding H3O plus, right? So what happens when I put water into acid is I end up with a hydronium. Again, the nucleophile here attacks the electrophile, the hydrogen. The oxygen is positive, but the oxygen can't accept any more electrons, right? Because it has a full octet. You have to attack the hydrogen, the one next to it. Right, that forms the carbocation. Then the water attacks that carbocation. Okay, and that's not, we're not going to leave it in this form, so we need to do one more step. So lone pair water is going to act as a base to deprotonate that. And notice we end up with water. Okay. So in the hydration of this alkene, we have the alkene acting as a nucleophile, right, reacting the electrophile, right, leaving group is leaving. So nucleophile attacks the electrophile, leaving group leaves. Then we form the carbocation. Water comes in, attacks that carbocation. We end up with this species here. We can't stop there. We got to deprotonate. So we need a proton transfer. And so we get a proton transfer to get us this product. That's kind of ugly H. So let me fix that. Okay. And notice what we end up with. Oops, and I didn't even draw it right. Make sure you get this correction. We end up with this as the byproduct, right? So we pull that proton, we end up with hydronium. Since we start with a hydronium, we end up with a hydronium. What does that mean as far as the H2SO4? Right? So if we end up with the same starting materials we had again, then that means this H2SO4 is just a catalyst. And this is important because we just covered dehydration of alkenes to form alkenes. So if we have an alcohol, I could take that alcohol and turn it into the alkene by using H2SO4, right? I can also take that alkene and turn it into the alcohol by using water and H2SO4. The difference between these is the amount of water, right? This is concentrated. There's no indication that water's been added. We know there's water in there because this is an aqueous solvent. Sometimes you'll see them put an AQ down here, but that's still concentrated. Here, we've got water prominent and then H2SO4. This is dilute. And sometimes you'll see it says dilute. It'll say, H2SO4 dilute. They'll be very specific about it. This gives us the product goes from the alkene to the alcohol. So we can take dehydration with strong acid to end up with the alkene, but we can take an alkene with dilute acid to do the hydration. Questions about this reaction? We can also turn alkenes into alcohols with hydroboration oxidation. Now, the thing to notice here is, where did I add my alcohol? Right? I've got two positions. I have a tertiary position and a secondary position. In hydroboration oxidation, where's the alcohol adding? The alcohol is adding to the least substituted position. This is known as an anti-Markovnikov addition. Okay, now I want you to think about this. Are we reversing the laws of physics and chemistry? Or did we reverse the way we're doing the reaction? Well, we're not going to automatically change the laws of chemistry and physics. We're going to have to go through the most stable carbocation. I mean, through the most stable intermediate. But maybe we're doing it in a different way. Notice we're adding the boron and the hydrogen first. So let's see what's going on there. So if we look at boron, what's actually the electrophile in the boron? Is it the hydrogen or the boron? Or borane, sorry, that's borane. So my electrophilic position is right here, right? It's got an empty orbital, so that's my electrophile. So when my nucleophile attacks my electrophile, right, it's reacting at the carbocation. It's reacting at the electrophile, right? Nucleophile attacks electrophile, not leaving group, okay? Now, one of the other things that happens here is that we have a concerted addition of the hydrogen. Okay? And we know that if we follow the stereochemistry. Let me change the stereochemistry here. We know that if we add this reaction, we're always adding to the same side, which means if we're always adding to the same side, and even in an acyclic reaction, that means that they must have both added to the same side. If they added at two different times in an acyclic reaction, this is a cyclic example, but if they added the same time in an acyclic example, then that means that we couldn't have free rotation. If we can't have free rotation, that means we get both of these occurring at the same time. So the nucleophile attacks the electrophile. The electrophile is the boron, but at the same time, we get the hydrogen going and reacting with the more substituted position, right? So if we think about that intermediate, because of the tertiary position, this is going to be the more partially positive. This is going to be the more partially negative, right? Partial positive, partial negative process. So that's the first step. So the first step is actually following Markovnikov's rule, right? I'm adding the electrophile to the more, to the, I'm adding the, I'm forming, right, the least, the most stable carbocation. So I've actually added my electrophile to the least substituted position to give me the more substituted position as my partial positive here. Okay, so I haven't changed the laws of chemistry. I've just changed what adds first, not the hydrogen, but the boron. Then the next step is oxidation. So we use hydrogen peroxide in a base solution, and that removes the boron by oxidation. Now, why is it important to know this is oxidation? because what's happening here is not that the OH minus is coming in doing a substitution, right? I'm not, this is not displacing that. What I'm doing is taking the boron and I'm actually oxidizing the boron and this group, right? So instead of having an electrophilic group, I'm having an oxygen there. The middle process here, and we won't go through the whole mechanism. What's happening is I'm going to be ending up with insertion. The middle intermediate here, transition state, is going to be, actually it's not a transition state, it's intermediate. What I'm going to be ending up with is the boron oxygen inserted between the boron and the carbon. What that means is wherever my boron is, so for stereochemistry, wherever my boron is, that's where my OH is going to be. So I retain the stereochemistry from the boron to the OH. What that means is, notice that I've added my hydroxide and my hydrogen to the same side of the alkene. Okay, so hydration, boration, both has an anti-Markovnikov product, but also what we call a syn addition. We've added both sides. Okay. All right. We're going a little fast today, so probably because I'm not looking out and seeing your faces. But I don't want to cover any more reactions, but I do want to kind of talk about how to study for this. One first tip, right, is mechanism. Draw the mechanism over and over again, right? And not necessarily just copy the mechanism over and over again, but anytime you have a reaction where you have to predict the product, show the mechanism of that reaction. That's going to help you understand the process that's going on and get away from memorizing the answer. That'll help whenever you get odd structures, right? If I show you simple structures like I've done today, and all of a sudden I go with something complicated, you'll have memorized the simple structure, but you still won't know what's happening. So when you're looking at a reaction, always do mechanisms. Two, put these into categories. And I want to misspell category. Right? So what if we see here today, we have formation of alcohols and we have reaction of alkenes. Right, so formation of alcohols, now I know I have two ways to form an alcohol. I can start with an alkene, add water and a non-nucleophilic acid. Oh, let's put that H on the other side. Right? And I know I can take an alkene, react it 2 steps. The BH3 means first step. Second step, I don't stop this reaction. Sometimes you can stop these reactions. This one you don't. You have to do both processes at the same time. You just add one reagent, allow it to react, and then you add the other reagent. Okay, and sometimes they'll call this aqueous. Right, so I have 2 formations of alcohols. If you start keeping this list, what you're going to do is you're going to start thinking about, what do I need to make, right? The other way to think about this is formation of alcohols. Here we have reactions of alkenes. Well, in this case, right, we have the HBr, right? So we have our halides. We could also do it as an HX type version. We have the alcohol. And by keeping these lists, it's going to help you understand what you have going on, right? And that's kind of ugly. So up to this point, we've really had really 5 really large groups of reactions.
So acids, bases, lots of things are having an acid base, right? We've got acid bases in our in these reactions we saw today. We also have substitutions, right? Substitutions, SN1 and SN2, big category of reactions, lots of variations there. And then when we go to eliminations, again, the two big areas, lots of possibilities. But what happens now is we're going to start going into these specific reactions, and we're going to start hitting them big. So the way to think about it is we spent a lot of time studying a big class of reactions. Now what we're going to do is start showing you lots of reactions. So by doing this type of characterization, this is going to help you keep them straight and understand the subtle differences, right? Okay. The other thing I would do is I'd make my own note cards, and don't buy note cards, make note cards. And remember, the way you learn things is to try and recall them. So if I was going to make a note card for the hydration of an alkene, on the front side, I'd put this, right? And if you want, you could put a question mark. On the back side, I put the reagent and leave off the product. Right? What this does when you're making these flashcards is you go through these, and the first one asks you a question: what reagents do I need? Well, your answer is on the back of the card, right? Then you can flip around and look at, okay, if I start with an alkene and I add water and sulfuric acid, what do I make? Well, I make an alkene. So you've made a double card that's asking a question. That recall of that information is going to be more important. If you just show the whole thing, you're not ever asking your brain a question, right? So by doing it this way, you're asking your brain a question, and you're doing this. So I make note cards. The other process of this that we've learned is that using a stylus like I am with my iPad, that writing process and the muscle movement actually helps me learn more than if I'm typing with my fingers. So if you're taking notes on paper or on an iPad or an Android device, and you're actually using all of your muscles to do that, you'll actually remember better than if you're typing in notes. So making your own flashcards, two things occur, right? One, by making them this way, you actually have, can you see that? This one right here. Is that the reaction you needed? Okay, right, so this is the anti-Markovnikov alcohol formation. Okay, so make those flashcards, and that's going to help you do that. Categorizing them, then that's what you can do, is you can study all the things that make alcohols, and then all the reactions of alkenes. Later we'll have all the reactions of alcohols, right? So you'll have formations of alkenes, reactions of alkenes. You'll have formations of alcohols, you'll have reactions of alcohols. So putting them in those classes will help you learn them better. And then making your flashcards so you can study these together. On Zoom or Roommate or such, one of the things I would suggest is making these flashcards and then going through them with each other, right? So that you can help train each other going through these. But that all starts with, every time you do a reaction, show the mechanism. All right, I went a little faster than I probably would have today. I don't want to add more reactions on. So let's go ahead and stop here.